let's continue with the cylindrical single pressure vessel. The previous one, we determine the hoop stress, which is sigma 1, and the equation is P over P times Ri over T. And then now we want to investigate the second type of stress, which is the longitudinal stress of this cylindrical tank. Longitudinal stress. When it's longitudinal stress, it means that for the tank, we cut perpendicular to the longitudinal, which we cut along the transverse of the tank, and from that we can be able to draw part of the tank at the cut. So in 3D again, and I also exaggerate the thickness of the tank. It's thin, it means like very small compared to the inner radius, but to make easy to visualize, we can make it big for the thickness here. And of course, along the material, we have, due to the pressure, we have the stress on the material along the longitudinal of the cylindrical tank, and that we call a sigma L, sigma L. So that is sigma L of stress. And of course, we also have the inner pressure, which is P apply from the fluid, and that we have, that one is P there. Then in hoop stress, sigma 1 equal to sigma hoop, and in this case it will be the book they call sigma 2, and for us here longitudinal to be more descriptive, and that it actually equal to sigma 2, another principal stress. So we, similar to the previous one, we want to determine the area for each for the longitudinal stress and the area for the inner pressure of the fluid. And as you can see, let me call again that A1, A2 are not the same on the previous one. For the single, that is the area A, and that is A1, and as you can see, it equal to the area of the outer wall minus the inner. So it, from that we can have pi, and the area of the circle equal to pi times the outer minus the area of the with the inner radius, I square, so that the area 1. And area 2 is the whole thing for the pressure, the inner pressure, and that is A2, and that A2 here equal to pi I squared, you can see, for the inner pressure. So let's do some math here before we apply to get the equilibrium equation for the to find out the longitudinal stress equation. So let's do some transformation here. We have A1 equal to pi, and we write out our outer radius minus pi inner radius square, and then we can do the associate P pi equal to R outer square minus I square. And if you know the a squared minus b squared is equal to a plus b times a minus b. So we apply in here, it's pi. So it will be r0 plus ri times r0 minus ri. So that algebra there. And as you can see, we can plug in. We don't want to have the too many unknowns, so we can replace the outer radius with the two variable here, which is inner radius and the thickness. So we can have pi, and as you can see, outer radius equal to the inner radius plus the thickness. So I can have that the r0 outer is equal to inner plus t and plus ri for the first one, and the second one is again ri plus t minus ri from that equation. So simplify a1, we have pi, the first one is 2ri plus t time the second one is t. So from that, as you can see, we can be able to write down it a1 equal to pi 2rit, right? 2i times t plus pi t squared. So that is the area A1. So now we can apply the equilibrium as we did before for the hoop stress. So we have an equilibrium equation, and this way we don't do the one for the y, but it along the x direction, longitudinal axis of the cylindrical. So we have sum of all the force in x direction, and equilibrium have to be equal to 0, and we plug that equation in. We have 0 now. It will be the sigma longitudinal times the area A1 minus the opposite P times area A2, because pressure or stress times the area, we have the load or the force. From this, I can have sigma longitudinal stress equal to P A2 minus over A1, and we can plug the A1 and A2 we already have in there. So we have sigma L equal to P A2 equal to pi I square over A1 equal to pi 2 RIT plus pi t squared. And we simplify the pi, then we will have what here? We simplify the pi. So we have sigma L equal to P I square over 2 RIT plus T plus T. Everyone see that here. So let me divide the top, the numerator, and the denominator by Ri, the inner radius. So I have it pi I over 2T plus T over Ri. T over Ri. And as you can see with the single, and by definition, to be a single, the inner radius, the ratio of R over T greater than 10. What does that mean here? As you can see, the T over Ri, it have to be less than 1 over 10. So very small compared to 2T. So from that, as you can see there, we can be able to t square, in this case it's t square, we have t square over there, so t square over I very small, so yes, the second component in the denominator is very approximate to 0 compared to the 2t. So from that we can ignore that component, so we can have the final equation is sigma L approximately equal to inner pressure P times the inner radius divided by 2t. And as you can see that we can plot the equation there. And we can also note the sigma hoop stress Pii over T, the longitudinal Pii over 2T. So we can have, what does that mean? We also see that the sigma longitudinal equal to sigma hoop over 2, or sigma hoop stress equal to 2 sigma L, so that have the relationship in the cylindrical single pressure vessel. And from that one, we can be able to determine the state of stress of this cylindrical single pressure vessel. So from that, we can be able to state of stress. Go back to the previous lesson, how to draw the state of stress. Basically, we have draw a block, a point on the body. Basically, it represents a square. Represent a square there. Square, and the hoop is the sigma 1, so we can have that is along the hoop of the cylindrical, and that is sigma 1 or sigma hoop, and that equal to sigma 1 in the book called that sigma 1, as you can see here. And the longitudinal, that is sigma L, and also sigma 2 if you read the book in there. And add the stress are the principal stresses, then you don't have the tau on that block. So, and with the Mohr circle, we can be able to represent that as well. So in terms of the Mohr circle, for this state of stress is we have sigma for the horizontal, and we have tau for the vertical, and we already know tau. And at the sigma 1, sigma 2, so we can locate where is sigma 1 and where is sigma 2, or sigma along the hoop. So we can have the sigma hoop is basically sigma 1, so that is the hoop stress, right? Hoop stress. And we also have the longitudinal stress, which is sigma L, and both, as you can see, positive in that equation. If you have pressure Pii over 2T, both are positive. Both are make the thing in tension, as you can see there. So when you have that, we can be able to draw the Mohr circle if we know 2 points. So the center, it will be here in the middle. And that we will have the circle, Mohr circle for this one. And at that point, at this Mohr circle, you can see when it have the principal stress, which is sigma hoop and sigma L, you don't have the shear stress on that plane, but we can be able to find out tau max for another plane from the master core. So with that, we done for the equation regarding to the cylindrical single pressure vessel.